So the logistic perceptron is a function of the following form. So I'll think about the one-dimensional case first. So it's going to be a function of a single variable. So we'll say f of x is equal to, and it's going to be, I'll say, so it's sigma of ax plus b, right? And so what is sigma? Okay, well, sigma is something called the logistic function. So sigma of x is defined as 1 over 1 plus e. Actually, let me use a different variable. Instead of x, I'll say u here, because it's really like I'm going to plug in this ax plus b to sigma. So let me use a different variable. So I'll say sigma u is equal to 1 over 1 plus e to the negative u. This is actually called the logistic function. Whoops, what did I mess up here? Sigma u, I missed a, so I'm doing LaTeX here, right? Okay, so here's the function. So what it is, it's actually a composition of two functions. First, it's just a line, right? Ax plus b, that's the equation for a line. Slope times x plus y-intercept. Composed with this other function called the logistic function. So let me actually define this. And I can do it pretty simply with an anonymous function. It's kind of a one-liner. So that would be 1 over 1 plus e to the negative u. And okay, so now let me just get an idea. So this is actually a function. If I want to look at it, this logistic perceptron, which is, again, it's the composition of two functions. It's the composition of just a linear. Actually, it's called an affine function, but you know, the line that you use to mx plus b with this logistic function. So together we call that the logistic perceptron. And yeah, so let's look at a couple examples of that. So let's say maybe a is equal to 1. I'll choose different slope and different y-intercept, and we'll see what happens. And I'll evaluate this over different x's. So I'll say np to lin space. So maybe my x is maybe I'll start from -2 to 2. I'll take 1,000 samples or whatever. And then let's just see what ends up being. So if I say y is equal to logistic of ax plus b, let's just plot it. And it says np is not defined. That's of course because I have to import this stuff first before I do that. Oops. Okay, so let's do that. And okay, so here's what it looks like. And let me also plot another line that will help us here. So I'll plot x dot size equals blah blah. Okay, so I'm going to plot this too. It'll help us to see, and I'll say -0.1 to 1. Okay, yeah. Let me get this even here. So okay, so first, I mean, we can look at if I look at this function here. So the range of this function, well, this would be a great exercise in Calc 1. I noticed that the limit as u approaches infinity of this function is 1, right? And the limit as u approaches negative infinity is actually 0. And so actually I'll choose a different version. If I make a little bit bigger, I see it looks a little bit more like this. So it kind of, it eventually saturates at 1 if I go to the right, and it saturates at 0 if I go to the left. Okay. And so it's kind of like, it's like taking a line, like this would normally just be a line, mx plus b, and kind of squashing it. Okay, if the line gets too big, I'm gonna, that's what the logistic function does. I'm gonna squash up to 1. If the line gets too negative, I'm gonna squash it down to 0. Okay. Now, what the heck does this have to do with what we were doing a moment ago? Well, okay, so look, if you look at this particular example of a logistic function, and I go back to separating these points on the number line, the function space that I was considering before was actually looked a little bit like the logistic function. It just jumped up very quickly. So this was like what we call a step function. This was like an ideal step function. The logistic function is kind of like a step function, but it actually is differentiable everywhere. Whereas here we have a jump discontinuity, right? So the logistic function is like kind of approximating a step function. If I make a bigger, then it starts to look more like a step function, but it's still differentiable. And that's going to help us in a moment to minimize, right? If you recall, just sneak preview the next video, but if you recall back in calculus, the way that we minimized functions was by taking their derivatives and setting them to 0 to find critical points, right? So we will eventually want to be able to take the derivative of whatever function we have in the process of doing that. And so it's helpful to have a family of functions that's actually differentiable. Okay, so that's one thing. Okay, but let's just explore this a little bit more. So one thing I want to do is let me go ahead and look at this data again and just kind of show you, maybe superimposed on top of that, what this would look like here. So yeah, let's kind of see how that does. So and what we're going to do is, because this function is not just 0 or 1, it has some values in between. What we'll say is everything above 0.5 we'll consider to be a 1, and everything below 0.5 we consider to be a 0. So you can actually view the logistic function as like the probability that our estimator, whatever function that we chose, thinks that this is in class 1. So if the probability is a greater than a half that we're in class 1, then we're going to say we're in class 1. So you can interpret this like probability. If the probability is less than 0.5, and especially if the probability gets close to 0 that I'm in class 1, then I'm probably should get a label of 0. So that's another way to look at the logistic function. So if I superimpose it on top here, let's just have a look at what that looks like. We see that, and I can play with the parameters a little bit to try to make that give a better fit. Now I haven't defined the fit exactly yet. I'm going to use a slightly different objective function. I'll explain that in the next video. But for now, I can at least kind of visually see, like, okay, everything above 0.5 here would be a 1. That means I probably need to move this over a little bit. Let me actually make B. So I'll make A, B, maybe 5, and then maybe I'm going to make B be a negative number, so this moves over a little bit. And maybe I'll move it over a little bit more. Okay, so that looks like maybe pretty good. So that's the idea there. Okay, now, but this idea of a logistic perceptron actually generalizes to higher dimensions. So we're going to try to address the cases that grid search would fail on. And so you can generalize this. So I can have a 2D logistic perceptron, which I would say is now this is a function of two variables. So like f of x, y, I could say that's equal to ax plus by plus c. So now I actually have 3 degrees of freedom in my function. I have an a, a b, and a c. And just to show you what that looks like, well, I have to plot it actually on a grid because I have 2 inputs now. I have an x and a y that I plug in here. And so let's look at an example. Let's say I took a equals 2, b equals 1, and c equals 1. And what I'll plot, I actually got to plot this on a grid because it's a function of 2 variables. So I'll plot, the x along this axis, y along this axis, and what I'm going to depict here is what the logistic function is as a color. If it's red, I'll say it's below 0.5. If it's blue, it's above 0.5. And so what you see here is much like we had, kind of a threshold here, like everything above 0.5 was to the right here, and everything below 0.5 was to the left. So you could say it's kind of like I divide the data in half with this kind of vertical line. We also, with this 2D logistic perceptron, we end up dividing the data in half. Maybe not exactly in half, but there is a line that separates us into a region that is less than 0.5 and then a region that's greater than 0.5. So we would say everything here would get a label of 1 and everything here would get a label of negative 1. And so with the logistic function, and yeah, actually, before I say that, I can show you, changing A and B, we'll move, we'll rotate this line, and then changing C, we'll translate the line. So we'll actually move the line in some direction. So changing A and B is going to rotate the line, and changing C is going to move that line around. And so in much the same way that we were trying to, with the logistic function, kind of match this idea of choosing some C to separate the data into parts, we can use the 2D logistic perceptron to kind of choose kind of a soft line that separates our data into two places. And so what we can do with so I can say that the kinds of functions that we can learn, so the kinds of data that we're able to capture with logistic perceptrons is data that is linearly separable, we say. Okay. So if I can put all the examples on one side of the line, all the zeros, and if I can put all the ones on the other side of a line, then we say that that data is linearly separable. So let's look at a couple examples. So let's say, let's say that I made some data. So maybe I'll call, okay, these are my zero examples. Maybe I'll say, let's say I'll make 100 zero examples between, let's see, maybe between, so 100 zero examples between x equals -1 to 0 and y is equal to 0, 1. So let's just plot that real quick, make sure I was right about that. Okay, so there's our zero examples, and then I could generate my one examples. Maybe I'll just put them on the other side of the line x equals 0. So if I were to plot my one examples following, then they would be to the right. So these are definitely linearly separable. I could draw a line x equals 0 and separate them. Let's just try to see what if we can find that line with logistic regression. So I made some code ahead of time here that was a bit cumbersome, but let's see if I can get it to work. So this is just going to plot the two classes superimposed with particular choices of the parameters for the 2D logistic functions. Let's say we'll start with a equals 1, b equals 1, c equals 0. Okay, and actually I tweaked the example a little bit, I tweaked the code a little bit. So let's start to play around with this. So if I started off with these parameters, a equals 1, b equals 1, c equals 0, I get this line here that actually it goes through the origin. So that's the line at every place on the logistic function that evaluates to 0.5. So that's the separation between positive, which would be above the line, and negative, which is below the line. And I'm showing again the logistic function evaluated there. And so this is not maybe the best choice of line because it labels a lot of negative examples as positive. So it got all those wrong. I don't know. So let's try changing. Maybe I make a -1. So now it looks like that. Actually, this is even worse. It got almost everything wrong because it said like pretty much every negative example was a positive example. And most of the positive examples it said were negative except for those ones. But I know if I make, let's see, if I make A1 and B0, then I get this vertical line. And that separates them perfectly. So everything above the vertical line is positive, everything below the vertical line is negative. I should probably shift over that line a little bit. So I changed the example a bit so my positive examples start at 0.5. Let's move that over a little bit. Oops, I went the wrong way. Classic mistake. To move it over, it's actually subtracting. Actually, maybe 0.2 is a good place. So yeah, this seems like a good place to put the line. We got 100% accuracy, all that, right? So that's nice. But there's certain data that we can't separate with a line. There's certain data that's not linearly separable. And so a logistic function will never perfectly capture that data. But we might be able to approximate it. But so a classic example that this doesn't do so hot on would be the following. So what I'll do is I'll generate a bunch of random samples, randomly distributed in the plane. So maybe I'll say, let's say 200 samples. And then what I'll do is I'll make the negative examples be, so I'll compute the radius of these samples, the distance from the origin. So I'll do that. I'll sum this up. Compute the radius from the origin, and I'll make the negative examples examples that have radius less than 1. So let me select all the examples with a radius less than 1. And then the positive examples will be all the examples with a radius greater than or equal to 1. Okay, so let me go ahead and try this one out. And so, whoops, I should greater than 1. And it would help if I said didn't have an extra equal sign there. Okay. All right, so I look at this data here, and let me zoom out a little bit. So I look at this data, and what I see is, okay, so the negative examples have a radius that's less than 1. So they're kind of in this disk of radius 1 here. And the positive examples are outside of that. Now, it's impossible. I can try as hard as I want to separate the positive examples from the negative examples using a line, and I'm just not going to be able to do it. That line is always going to be cutting through part of the circle. And so, just no matter how hard I try, I'm always going to have some stuff that's wrong here. And so we would say, okay, this is not a good model, not a good family of functions for separating this data. Like, the best we can do, it seems to be like 50-50, pretty much. I mean, yeah, I could even try to put this all to one side, right? I could say, okay, let me be really extreme about it and put that line all the way over here. And so everything is above the line, but then I get all of the negative examples are wrong because I say everything's positive. So this is probably the best I could do, 50% accuracy. Otherwise, I'm like dividing the circle in half, somewhat. So yeah, that is not good data. Usually we'll see something in between, kind of like, or there's a lot of examples where not usually, but many examples where we'll see something in between where, like this example. Technically, this is not linearly separable in one dimension because we can't actually choose a vertical line that splits this completely in half because there's a little bit of overlap here. But it's pretty good, right? Like, there's not much overlap between the classes. And so, like, I could take an example like this, and I could make, these overlap a little bit. And so, yeah, you can see these overlap a little bit, but I can actually do pretty well if I put the line, let's say, around here. So that's not bad. I can get 80%. This is probably a pretty good choice here. So I'm going to miss some near this margin, near where they overlap. They're going to get incorrectly classified. But I'll do pretty well on. So let me get this fully in range here so you can see. I'll do pretty well on most of the examples. See, I'll just miss. Actually, could probably move this to the left a little bit more. I'll scooch it over. Okay, so I could get up to like 88%, right? So it erroneously says that some of these negative examples are above. Now I'm realizing it would probably be clear if I switch the color map here. Let me just so that the colors match. I'll do that for posterity here, and it'll be in your notes. But yeah, I should probably actually reverse the red and the blue here. So let's look at these again real quick. Okay, yeah, this actually makes a lot more sense. So anyway, you see, like, yeah. So when it gets red, it's classifying those as positive. When it gets blue, it's classifying those as negative now. And So I see, there's some negative examples that jump over the line and are classified as positive. There's some positive examples that jump over the line and classify as negative. If I scooch this line just right, I can probably get a slightly higher accuracy. I don't know. Yeah, I'm getting around 85, 88 or so. So again, not perfectly technically linearly separable, but pretty good. Okay. But this is definitely, you should not be using logistic perceptron on this at all. Okay, so not every data set is appropriate for this model function. So I just want to ask you a question real quick about, just to test your comprehension about what's linearly separable and what's not. And then I'll move on to talking about the loss function.